So I shall be talking about these precipitation type models and their significance in understanding gaseous halos across mass scales. And I thank the organizer for organizing this meeting in such a wonderful manner that everyone has, something to get out of it. I really thank them for putting in all the hard work and arranging it beautifully. And this is our institute where I work, so you're all welcome to visit us as soon as it is possible. Okay, so I'll be talking about a very simple and stripped down model of the circumgalactic medium. And so here is sort of my cartoon. And this is mostly motivated from cool core clusters, because that's where the observations of the volume filling phase of the hot phase is easily done. So we know that the hot phase in galaxy clusters and even in cool cores is in rough hydrostatic balance. And in the cool cores at the center, the cooling time is shorter than the Hubble time. So that means, right, and we don't see any signatures of cooling flows in the sense of young stars and high star formation rates. So that means feedback heating due to AGN jets is somehow preventing the central gas with short cooling time from cooling catastrophically. So, so these are sort of the main elements of CGM halos, and mostly motivated from intracluster medium. You have dark matter gravitational potential, you have hydrostatic volume filling phase, and you have cooling and heating due to feedback. Now, so these are sort of the simple equations. So this is the hydrostatic equilibrium in a dark matter gravity, which applies for the background diffuse gas. And thermodynamics is extremely important, okay? And this is the entropy equation for a fluid element, which shows that the entropy can be lost because of radiative cooling, which is this term, and you can increase the entropy or internal energy because of dissipative heating, irreversible heating, which is represented here by this Q plus term. And it's important to note that this is not a state function, unlike the cooling function, which is a function of density and temperature alone. This can be a function of space and time, right? When we study thermodynamics, we write d bar q equals du plus pdv, right? D bar q is important, which means that you cannot write q as a state function. Now here, I am showing a typical collisional ionization equilibrium cooling curve, and it's useful to keep this in mind because this applies to most of the topics that we are going to hear about in this conference. So here at very high temperatures, so this is log T, and this is 10 to the 8 Kelvin, 10 to the 7. So at very high temperatures, all the gas is ionized. You have free cooling. At lower temperatures, ions are not fully ionized, and you can have atomic transitions of oxygen and so on. And below 10 to the 4 Kelvin, hydrogen starts recombining, and you cannot excite atomic transitions, and there is a steep fall in the cooling curve around at 10 to the 4 Kelvin. So at this temperature there is also photoheating, which sort of imposes a floor of 10 to the 4 Kelvin, which is the motivation for imposing this floor in a lot of simulations that we have heard about. Now, one thing to note here is that all these temperature regimes are formally thermally unstable to small temperature perturbations. Now, I already mentioned that the cluster cores can be thought of in rough thermal balance, the balance between cooling of the ICM due to these atomic and plasma processes, and also heating due to feedback. So this idea of thermal instability is not very new, and it goes long back, but most of the older analysis was in the context of a background cooling flow, in which the background gas cooled and flew towards, and sort of flowed towards the center. And in such a background, which is evolving on the cooling time, the density perturbations do not grow. And these are the papers which sort of were using this model. But the presence of these bubbles, AGN bubbles, show that, heating is also very, very important in galaxy clusters. And because of the lack of cooling flow, one should consider thermal balance as the state at which around which you perturb your system, right? So the earlier models were perturbing the wrong equilibrium, basically. And an equilibrium with thermal balance is more motivated, at least for galaxy clusters. So here is actually a simple 1D simulations carried out about 10 years ago now, which shows development of thermal instability in a periodic box. And in this black line shows the initial density perturbations, and this dotted red line shows its linear growth. And this is basically the entropy mode, which is thermally unstable. And these scales of interest are isobaric. That is, the sound crossing time across the modes is much shorter than the cooling time. So this actually applies to the galaxy cluster cores very well. You also see this dashed blue line, which has thermal conduction in it. The role of thermal conduction is to wipe out perturbations at small scales. And this scale below which perturbations are wiped out is called the field's length. Now this is the linear state, and non-linearly this is what happens. These density, and so these are isobaric. So wherever you have high temperature, you have low density. So these high density peaks, low temperature peaks become nonlinear. They have shorter cooling time, and you get these nonlinear structures. So this is hot diffuse background phase, and this is dense phase, and this is with thermal conduction. But without conduction, you have many more small clouds as shown here. Okay, so in this setup with periodic boundary condition, you always have multi-phase gas after a thermal instability timescale, which is of order comparable to the cooling time. And since the density, since the plasma is compressing in the dense cool phase, this cold phase is likely magnetically dominated in reality. In these simulations, we are actually imposing a temperature flow at around 10 to the 6 Kelvin. So that's why this is not at 10 to the 4 Kelvin, but at a higher temperature. But that was just so that we can resolve the cooler phase a bit better. Okay, so this setup did not have any gravity. Now the question is, what happens if you have gravity? Can you explain these magnificent H-alpha filaments that you see in Perseus cluster by invoking local thermal instability and global thermal balance? So here is actually a toy model in which we have included gravity. So this is like a dark matter halo. You have gravity acting towards the center, and in every shell we are balancing heating and cooling, right? But this thermal balance is not point by point. It does not apply to every point, but only in shells. So the slightly dense regions in these shells can cool faster than their surroundings, and it can in principle become multi-phase. So this is one of the ANSATs, which is motivated from observations of cool cores. And we have hydrostatic equilibrium where gravity is due to dark matter. So the question is, what does this model give us? Does this also give us multi-phase gas as our periodic model? So what we see in this model is, right, so here is actually a galaxy cluster, a model galaxy cluster with small perturbations shown on the left. This is density, log density in CGS units. And you see the central portion of the cluster is dense and cool. And we let this thermal balanced model run. And what we see is that there is a very, very important parameter that we sort of notice, that the ratio of this cooling time to the free fall time in the background determines whether this simple ansatz of shell balance, shell thermal balance can give rise to multi-phase gas or not. So whenever the cooling time to the free fall time is less than around 10, the dense regions condense and form these nuggets, which are at 10 to the 4 Kelvin, at the temperature of the stable phase. Okay, so these condense out. Whereas in the other case, where cooling time to the free fall time is big, greater than 10, like 20, 30, then we don't see this condensation, even if we wait for many, many, many cooling times. So this suggests that there can be some sort of self-regulation going on in such systems where Tcool over TFF, where cooling time is measured in the background hot gas, is maintained in this state where the cooling time to the free fall time is greater than 10. And otherwise, what would happen is this gas would become multi-phase and result in condensation, and these cold clouds will sort of slowly fall towards the center of order the free fall time and give rise to feedback fueled by cold gas. Now, this is actually a very, very simple experiment, but it has far-reaching consequences. So this suggests an ansatz for the state of the hot CGM. The ansatz is the following, that at large radii, the halo should have a cosmological profile, like some sort of r to the minus 2.5 or something like that in density. And as soon as one reaches a radius, so you start constructing these models at the outer boundary, and you impose hydrostatic equilibrium with a given density profile. So you can actually start building it. But at some point, you will hit a radius at which the ratio of the cooling time to the free fall time hits 10. And this is the radius where you expect the hot gas density to be regulated. And here we put an ansatz that within this radius there is a core, and you can make a choice for this core. Like you can have an entropy core or a Tcool or TFF of 10 core. And so these are actually models constructed for different halos, ranging from a Milky Way mass halo here at the bottom to a 3 times 10 to the 14 solar mass cluster here. So these lines, the dotted lines correspond to a Tcool over TFF of 10 core, and the solid line corresponds to an entropy core. And what this suggests is that the more massive halos, like clusters, should have denser hot gas in their center. So this is partly the reason that galaxy clusters emit so profusely in X-rays, whereas lower mass halos like the Milky Way or even groups do not emit as much, because their densities, the hot gas densities, are lower. Of course, their volumes and masses are also lower, but the density is also low. So, so this is actually very, very profound, and it actually is based on a very simple model, which is this Tcool over TFF, the significance of this threshold. So this is actually the original precipitation model, and there has been a lot of work on this type of models, notably by Mark Voigt and his collaborators. And in fact, for the Milky Way, the whole CGM is the core. Basically, the cooling time to the free fall time ratio, even at the virial radius, is smaller than 10. So the whole CGM density has to be modified. And this is what happens in these, the bottom lines here in the dotted line and in the solid line. And this sort of an argument should apply to even other coronae like AGN and the solar corona, in fact. So what about observations? So here I have actually put together this graph from Mark's 2015 paper. Here on x-axis I show radius and the y-axis shows the cooling time, and this magenta band shows this cooling time to the free fall time ratio between 5 to 20. So this is the zone where you expect multi-phase gas to be present according to this precipitation type models. And indeed, so what is shown here in profiles are data from accept sample, and these blue ones indeed show evidence for cold gas in H alpha or in far infrared. Okay, whereas the red ones, which have high, longer cooling times, do not show multi-phase gas. So there is some evidence that something like a T-cool or TFF of 10 is respected by real systems. So in fact, there is much more work done by Mark, which shows observational comparisons across halo masses. Now, one of the questions is why thermal instability does not lead to multi-phase gas for large cooling time to the free fall time ratio. And it's a fundamental and a subtle effect. Okay, so here is like our toy atmosphere, which is hydrostatic, and there is gravity. So you consider a blob here, right? So you can consider two sort of limits. One where the background atmosphere is strongly stratified. So this blob is actually oscillating very, very rapidly at the local Brunt-Weissela time scale. So what these oscillations do is they excite gravity waves in the neighborhood of this blob and limit the amplitude of this perturbation. So the driving by thermal instability wants to make this multi-phase, but this driving of internal gravity waves in the surrounding medium balances this driving. So this system can actually saturate at small amplitudes, delta rho by rho less than 1. So you never see multi-phase gas even if you wait for very many cooling times. On the other hand, we can also consider this scenario where the background is not very strongly stratified, that is the Brunt-Weissela timescale is long. Even in this case, as the blob falls, even though there are no restoring forces, you have like local shredding of this blob because it's moving relative to its surrounding. So this is sort of like a local cloud crushing setup where the density perturbations are small. Okay, in both cases, you can suppress formation of multi-phase gas if the background cooling time of the free fall time is larger than this threshold. So Mark has actually worked on this aspect a lot as well to elucidate what's going on in here, and you can actually check out his latest work that he has just now posted on the Precipitation channel. Now, what about more complicated situation, right? For example, in cosmological simulations. So there, this NSADs of thermal balance in shells and so on is of course clearly not valid. So here actually is a snapshot of magnesium-2 column density from Dylan Nelson's work recently, and it shows a lot of like tiny clouds, and this multi-phase, so this is dense cold gas, and the origin, this multi-phase gas has multiple origins. Some of them are associated with wakes of galaxies, and some are like long-lived dense things which were stripped off from cosmological filaments and so on. But what you see here is that the cold gas is actually ubiquitous and has a very large area covering fraction, comparable to observations. Similarly here, you have a situation from Yuan Li's jet simulation which show like in early phases, the multi-phase gas can actually be stimulated along the jet directions. Now, so this is actually a complicated complication that has to be incorporated in multi-phase condensation. So this was a little numerical experiment that was done by Prakriti Pal Chaudhary, where so in addition to those thermal balance in shells, she seeds density perturbations, okay? And what is shown here are a series of numerical experiments. The x-axis is the amplitude of density perturbations, and the y-axis is the minimum of cooling time to the free fall time in the diffuse gas profile. And so this is sort of like a threshold for condensation. So if you're above this threshold, you will have no condensation, and if you're below this threshold, you have a tendency to become multi-phase. The atmosphere can become multi-phase. So the key point to notice is that it has this hockey stick shape. So when your delta is smaller than 1, so when the perturbations are linear, then you sort of recover the cooling time to the free fall time threshold of order 10. But if your density perturbations are non-linear, then you can have multi-phase condensation even when the cooling time to the free fall time is larger. And this is what we see in some of these cosmological simulations and in AGN simulations that I showed from UMON. Now here is actually the x-axis here is time over 5 gigayears. So what's shown here are some important quantities from AGN jet so from ICM simulations with kinetic feedback jets. And what you see is the presence of these cycles. So this magenta is the ratio of cooling time to the free fall time measured in the hot phase. So when this cooling time to the free fall time threshold drops, right, you have a lot of cold gas formed that sort of funnels cold gas to the AGN, and you have an increase in the jet power, right? So you have these episodes of cooling and heating. And so, for example, here at this time, the cooling time to the free fall time is greater than 10, and you don't have any cold gas. So there are cycles. In more realistic systems, you expect cycles of cooling and heating. Okay.
Thank you, Prateek. I have to stop you here. Okay. And so I think we need to continue your discussion over in the precipitation breakout room. And so it sounds like, this is an incredibly rich subject, and that was a really great tutorial. Thank you. I know you had 2 slides left, but I think that was, a wonderful
that's fine.
And so the precipitation tutorial room is open.